How are we doing? We are going to continue this journey on the 1998 AP Calculus AB. We finished Section 1, Part A. We are now on to Section 1, Part B. We are going to do problems 76 through 82. And Glory be, we can use a calculator. If you haven't already, give me a like anytime, any of those videos. Follow me so you know the next time I put a video up, you'll get that notification. The like just helps me because, you know, I'm self-conscious like that. All right, let's get started. 76. The graph of the function f is shown above. Which of the following statements about f is false? I don't know what it is about students. When it's true or false or the directions, you just see this and you just go right to the multiple choice. I think calculus students are slightly different, but 4 of those 5 are going to be true. So don't circle the first true one, circle the first false one. And A is absolutely false, okay? F is not continuous at point A. All right, let's do a highlighter. Here's where x is equal to a, right there. It is not continuous. There's a hole, okay? There's a maximum at a. Yeah, that's a relative max, that point. That's true. X equals a is in the domain. Yeah. At a, you have a valid point. So that's true. The limit as I approach a from the right is equal as I approach a from the left. Yeah. If I approach a from the left and I approach a from the right, whatever y value is here is the limit. And E just says there's a limit. If D is true, that's proof that E is true. Did I have to go through all those? No, but you know. Otherwise, this question would have taken 2 seconds. All right, done. 77 oozes calculator. How do I know? Look at our multiple choice responses. They're all 3 decimal places. You are not going to calculate that with your brain. So 77 says, let f be the function given by f of x equals 3x. Yeah. F of x equals 3e raised to the 2x. And let g be the function given by g of x equals 6x cubed. At what value of x do the graphs of f and g have parallel tangent lines? All right, let's do calligraphy pens here. Boom. Parallel tangent lines means the slopes are the same. And in calculus, slopes are derivatives, and same is equal. Okay, so where are these derivatives equal? Well, you know what? I want to try something here. The derivative of f of x is 3e to the 2x times 2. All right? This is a constant, stays the same. Anytime I take the derivative of e to the x, I immediately rewrite it, then multiply it times the derivative of the exponent. So that's going to be 6e to the 2x. G of x, the derivative is just 3, bring that down front, 6x squared. That's 18x squared. I'm going to graph those into y1 and y2 and see, okay, and see where they're equal. All right? You know, I was going to try something else in the calculator graphing it, but you know what? I'm not going to now because I don't think it'll work anyways. So I'll just keep that little nugget to myself. All right, so we have 6e to the 2x and 18x squared. Yep, that should be squared. Squared, there it is. If I graph that, I get this wonderful, wonderful drawing, because you know how I feel about graphs and drawings. I love them. I love them so much. While this little thing is spinning, that means the calculator is still working. And the spinning thing is done. They intersect right here. Okay, I am going to zoom in. I'm going to create my little box here because I love my box almost as much as I love my drawings. Boom, move over, move up. Yeah, right there. Boom. And we're going to get a much more clear. Did I have to do that? No. Is it easier for you to see on your like mobile device, your cell phone, your tablet? Definitely. Definitely easier. Now, I don't know. This looks like it's just short of midway. Midway's here, so maybe 0.4 or 0.3, somewhere around that in the negatives. All right? So, but I don't have to guess, because if I go to second trace and pick intersection, yep, okay, okay. That's cool. I see what you did there, calculator. I mean, I didn't, but I get it. I just go close and hit enter 3 times. 1, 2, 3. There you go. Boom. I got to cover the work. Negative 0.39. That 0 will become a 1 because the number after it is bigger than, is 5 or bigger. C. 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 78. Oh, related rates problems. Love them. The radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. In terms of the circumference, what is the rate of change of the area of the circle in square centimeters per second? Okay, so let's just figure things out. Okay, the radius of a circle is decreasing. So if the radius is decreasing, that's the rate of the radius, dr, okay, with respect to time, dt, okay? So if it's decreasing, that means it's negative 0.1, okay, because it's decreasing, it's going downward, okay? And I don't mean in terms of direction, but in size. Okay, so in terms of circumference, that means C is going to be in our answer. And if you look, C, 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 okay? What is the rate of change of the area? I need to find dA dt, okay? And in this answer, I'm going to have my C involved in here. That's something with a C. All right. Okay, now we got a direction here. So first thing I need to do, if I'm going to take the derivative of the area, well, I need to know what the area of a circle is. That's just pi r squared. Okay. All right. Let's take the derivative of said formula with respect to time. Pi is a constant, that'll stay. R squared, the 2 comes down. That becomes r to the power of 1. Again, we don't have to write those ones, do we? We don't have to write them if it's just the power of 1. Oh, there we go. We're still there. Okay, now, it's a related rates problem. It's like doing things implicitly, meaning anytime I take the derivative of a variable, I need to write dr dt right next to it. Boom. All right. This is the rate of change of the area as we know it. We need to get a C in there somehow. And I know that negative 0.1 is my dr. So right now, that's negative 0.1. And then we have 2 pi r is my dA dt. Now, some of you, this might jump off the screen. Those of you that loved geometry, you know that cherry pies are delicious and that apple pies are too. Those are the formulas for the circumference and area of a circle. I need to get this into my equation down here. The thing is, I have r, not d. So isn't the diameter just twice the radius? So my diameter is really 2r. Okay, that's not bad. That's not bad at all. So I'm going to take my c, and instead of saying pi times diameter, in for my diameter, I'm going to put 2r. So circumference can really be written as 2 pi r. You see the connection now? If only I had a 2 pi r somewhere, oh, look. I can substitute in the c for my 2 pi r. Oh, isn't yellow overgrown? I guess if I do the yellow this way. Wow. Interesting. Anyways, here we go. C times negative 0.1 is negative 0.1 C. That is the change of rate of the area with respect to time. Choice B. 79. Well, this is going good. There'll be a problem that's going to take a while coming up. I'm looking at it maybe 82, but we'll get there. The graphs of the derivatives of the functions f, g, and h are shown above. Those are the derivatives, not the original graphs. Which of the functions, f, g, or h, have a relative maximum on the open interval from a to b? All right, first of all, let's do some things here. Let's go purple. This is f prime. This is g prime. And this is h prime. All right, there we go. So in order to have a relative maximum, it has to go up to down, which means my derivative needs to go from a positive to a negative derivative, okay, around a slope or derivative that equals 0 or undefined, okay? Now, let's kind of block all these off from A to B. Here's H. Wow, here's B. Here's H. Here's B. Man, I am not. There we go. Finally hit one. Okay, from A to B. Move this over. Just because I'm just peculiar. This one is way off. Come on. There we go. Okay. And if these all represent the derivatives. Okay, there's a reason that I make the y-axis the derivative. The derivative is whatever the y value is. Okay, the y's are all positive above the x-axis, and they're all negative below the x-axis. And where they touch the x-axis, your derivative or your y value is 0. So let's go here. Let's see if we can make that blue. Oh, we can. There's our x-axis, okay? Be nice if, there we go. All right, so anything above that blue dashed line is considered a positive derivative or positive y value. Anything below that blue dashed line is considered a negative derivative or negative y value. Anything that touches the blue line is considered a 0. Remember, we want a 0. Okay, here's it touches 0, touches 0, touches 0, touches 0. And this H, this one right here, it never touches the x-axis. It has no zeros. All right? But we want to go from positive, okay, so positive, 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 positive slope, okay, because it's above. Positive, positive, positive slope because it's above the x-axis. This is all positive. Okay, right now, if I have an all positive slope, the graph of h is just going to be constantly increasing. So it will never have a maximum. So it can't have h in it. H. All right. Now let's take a look at the negatives. Anything below the line is negative. It's negative here, negative, 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 negative. Okay. Remember, I want it to go from positive to negative as I go left to right. The only thing that goes positive to negative, wait a second, maximum, what am I missing? Oh, man. Woo! Look at this little tail right here. It's negative right there. I almost missed that. Why is that important? Purple. This goes negative 0 to positive. I don't want that. I want positive to negative. Right here on F is the only place that this happens. Okay, so F is an answer. It can't be G only. Okay, well, let's see if it's f and g. This changes once from negative to positive, not positive to negative, so it's not g. Woo! Good thing I saw that tail. Sometimes you write so much on these things that you miss little details. The answer is A. Number 80. The first derivative of the function f is given by f prime of x equals cosine of x squared, or I should say cosine squared of x, over x minus 1/5. How many critical values, okay, how many critical values does f have on the open interval from 0 to 10? I don't care about anything outside 0 to 10 on the x-axis. Critical values, okay, are where mins and max happens, all right? It's where your slope changes. Okay, it's just like the previous problem, except we don't have the graphs here. We have the first derivative. But the previous problem, we had the graphs of the first derivative, right? And that's how we can tell where our mins and maxes happened. And we're going to do the same thing here for this problem. So I'm going to graph that. Okay, critical values, okay, that's when you change slope. Okay, so you can go from positive to negative or negative to positive. Okay, it doesn't matter. So the first thing I'm going to do is I'm going to graph that equation. All right, and in the calculator, you cannot put maybe, and I'm changing my thought process here, maybe this question is just testing you on how you write cosine squared of x, because, bam, you can't put the 2 next to that s for cosine. You see that? So I'm going to put cosine of x and then square the whole thing. All right? I always tell my students to write it like that, because when I have to take the derivative of it, the power rule is much easier to do. Okay? So it's a cosine of x all squared over x minus, we got another fraction of 1/5. And the beautiful part is, on my window, I just want to go from 0 to 10 on the x. I don't care about anything else. In the y, let's go from -2, negative, let's go 5s. Let's graph this bad boy. Here we go. Okay. It looks like it definitely crosses here, here, and here, but I don't know what's happening here. So let's kind of zoom in a little bit. Instead of zoom box, I'm going to change my window. Let's just go from -1 to +1. Let's see if that helps. We're going to shrink our up and down. See, now it becomes a little bit more obvious. Cross, cross, it crosses the x-axis, and it never crosses again. It never crosses again. It doesn't ask me to identify the points. It just asks me how many points are critical values. Again, if this is the derivative, no, Lord. If this is the derivative of f, okay, or the slope, they're all positive above, positive, 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 and they're all negative below. So right there, there's one change. Then right there is another change. Right here is a third change, but then it never changes again. Okay? There are 3 points here, here, and here. 3 points. I don't know what the x values are, but you know what? It's not asking me what the x values are. It's just asking me how many. So the answer is 3. There are 3 critical values. 81. 81 says, let f be the function given by f of x equals the absolute value of x. Ooh, that looks like a v. Absolute value. Value looks like a v when you graph it. Okay. Which of the following statements about f are true? Again, Earlier they asked us what was false. Now they're asking us what's true. If I were to graph this, the absolute value function looks like that. It goes up and down forever. All right? And it says f is continuous at x equals 0. Okay, so they're just looking at this point where x is 0, right here at the origin. There's a point there, right here. Is it continuous there? Yes. There's no holes. There's no breaks, jumps. There's no asymptotes. That's true. So 1 has to be in the answer. Good. No. No. Good. No. So it's only 1 or 4, I guess A or D. All right? So that means 2 has to be false by default. Well, let's look at that. F is differentiable at x. No. Corners, cusps, vertical tangent lines. Those are 3 scenarios that are continuous but are not differentiable. Okay? If something's differentiable, it has to be continuous. But it's not true the other way around. Just because it's continuous doesn't mean it's differentiable. Doesn't mean you can take the derivative of it. And here are 3 examples. In one of those 3, the corner is in our graph at 0. So 3 says f has an absolute minimum at x equals 0. This point right here is definitely a minimum, so that has to be true. So it's 1 and 3. Bam. Oh, that was a nice one. 82. If f is a continuous function and capital F prime of x equals lowercase f of x, for all real numbers of x, then the integration from 3 to 1 of lowercase f of 2x dx is right away. And I try and tell my students this, whether they listen or not, that's on them. Let's go orange. I'm in an orange mood here. Ooh, I want the thinner one, though. Orange. It's almost fall time. I mean, if you look, it's October 3rd on the bottom right. So, you know, it's getting fall-y here in the Finger Lakes region of New York. Anytime they give you this, I immediately make this substitution. Okay? So, if little f is capital F prime, I do that right away. I make that right away. I make that substitution, okay? Because it's going to come back to bite you in the buttocks. And look at all my answers. I need to get a capital F in there anyways. So you might say to yourself, well, I have the capital F with the derivative, but not the integral. Oh, okay. Okay, I see you. But let me explain something. This is what I want. This is what I have. This is one derivative away, right? Which means if I go backward and integrate, I get the original. That's exactly what I'm doing. Okay, so I'm still going to use this. I mean, this model comes back time and time and time again. All right, so let's go a little, ooh, let's go with a soft green. All right, that's a pretty green. All right, so here's the thing. I've got to use u sub here. You know, if I want to integrate capital F of x, it would give me f of x, but I got that 2 in there. So I'm just going to make this easy and say, well, what if u is 2x? Okay, that means du will be 2 dx. I only want to substitute in for the dx, meaning I want to get rid of that 2. So I'm going to multiply both sides by a half. Ooh, look at the difference in greens. This goes with this. Now, 1/2 du is going to get substituted in for dx. Let's get that cool green. So, du, my 1/2 I put on the outside. I always put a constant on the outside. The integral of f prime of u, because in for 2x is u, don't you forget to change your bounds. Right now, these are x's. X equals 1 and x equals 3. But if my upper bound is x equals 3, then 2 times 3 would give me 6. So my new upper bound is going to be 6, And my lower bound actually goes on 2 times 1 is going to be 2. These are my u bounds. The 3 and 1 were my x bounds. Okay? These are my x bounds, but I want the u bounds now. So 6 and 2. All right, so now let's integrate this. If I have, and this is f prime, let me just make that clear, and I go backward, I have f without the prime for my upper bound minus my lower bound, and oh, by the way, I still have my 1/2 on the outside, right? All right, let's see if we got an answer there. Ooh, I see it. What they did, another folly color, I guess the orange, maybe the red, light brown, lighter brown. They distributed the 1/2. So it's 1/2 capital F of 6 minus 1/2 capital F of 2. And that there, friends, is my final answer. Choice E. Yeah, man, that's E. And we're done. Again, like these videos, that helps me out as an educator, as a person, and as someone who just really wants friends. Like the video, follow me so you get a notification when I do the next part of section 1, part B, and I upload it. You're going to want to see it. I'll talk to you later. Have a good day, and keep on calculusing. Keep on calculusing. Keep on mathing. Do things with numbers. Do great things with numbers. Bye-bye.